Ally PLM.
Hello and welcome to today's Lunch Bite. In this Lunch Bite, we're going to be taking a look at what is new in Solid Edge ST10 Part 2. Our agenda for today's Lunch Bite is we're going to take a look at some of the add-ons that were included with ST10. We have some new functionality with generative design and reverse engineering. A new simulation analysis software called FlowEFD. We'll take a quick look at that as well. We've included some new technical publications as well. Built-in data management has been enhanced with more functionality here in ST10, and then also the new Solid Edge portal. The first thing I want to get started talking about is generative design. So welcome to the next generation of design. If you consider kind of the traditional methods of designing, you're going to design your model to be as strong as possible to withstand the stresses that are going to be applied to it, but you want it to be as lightweight as possible to help save on material cost. Once it's designed, you usually then run a stress analysis on it to make sure that it meets all those goals that you've set for the part. Now what we can do with generative design is we spend kind of a minimal amount of time designing the actual features on the part, get more of an overall shape created, add in a couple features like mounting locations, and then we go in and let generative design create the model for us so that we don't have to spend as much time doing the design work. We again set up those specific mounting points, we apply some different forces to it, and let the software develop the part for us. So this should save time on creating models, and it also does the stress analysis at the same time for us. And ST10 Generative Design will have its own ribbon tab. All the commands are going to be inactive until you go in and create a new study. If you haven't applied a material yet, it'll just ask you to apply one. And then we have also a docking window on the side of our screen. This is going to have any of the loads or constraints that you've applied to the model listed over here. If we take a little closer look at some of the options in the menu, we have a design space option. This is going to be available if it's a multi-body part. If it only has a single design body present in the file, then we don't need to use this. But again, if you have a multi-body part, you can go in and pick which body you want to do the analysis on. Then we can go in to determine what regions we want to preserve. This is going to be things like faces or holes that we want to preserve so that they don't get optimized, meaning we don't want it to remove any material from that location. And this is mainly going to be things like mounting holes, mounting locations like that. There is a setting for manufacturing. This is going to be used maybe if this is going to be a cast or injected molded part. We want to be able to get this out of the mold so we can determine which way the overhang prevention should be, and we can remove any internal voids as well. Next, we can go in and apply our loads and constraints to the model. So we get to choose, just like we would in simulation, the types of forces and constraints that we want to apply to it. In the picture down at the bottom, we've applied two forces to the outside faces, pulling away from the model, and then you see this is the finished generative model that we have here. Also in the middle of the hole, that is a preserved region, so we notice the hole maintains its shape and we have a nice little offset distance away from it to keep some thickness around it. Once you get all your loads and constraints applied to the model, we then generate the study. When you hit the generate button, we have an options window that will pop up. We can set this study quality. We can choose our target mass, what mass we want to end up with. You can either do that by a percentage or type in an actual target mass value. And then you have things like yield stress, allowable stress, and factor of safety down at the bottom as well. When you run the generate button, it'll go through the process of creating the generative design model using all those input values that you put in there. You'll get a little feedback when it's done, just telling you, maybe some features couldn't be optimized, it was too small of a face, and so on. And if it fails or can't optimize it, it'll tell you that as well. Once it's done though, we can show the results. Again, this is a stress type analysis, so we get to actually see those stresses on the finished generative model. So let's go ahead and take a look at how this works. For our example here, we're going to be taking a look at the Bernina sewing machine, and we're going to switch our display configuration to take a look inside at the main frame. And what we're going to do is create a generative design study on one of the parts. And I've got kind of a base part designed already that's going to fit between all of these components, so I'm going to turn that on. And we see again, it's really just a basic shape. We've got some of the holes built into it. where we need to maybe mount it or have some of the shafts go through. And what we want to do is create a more lightweight design, obviously to save on some material costs. So I'm going to edit into this part file. We'll go ahead and hide those background components, and you see up here I'm already up on the Generative Design tab, so this will be included in here for you to use. I've got a material applied. We've already started one of our studies, so we can go through then and start to define maybe some regions we want to preserve. So if I do the Preserve Regions command, we get to pick either faces or entire features if we want to preserve. So I'll just go in with the feature option, pick some of the holes in here that I want to preserve. Again, maybe those are some sort of mounting holes, or these ones over on the side, or where some of the shafts run through. So I just want to preserve those. Next thing I can do is apply maybe a force. So we're going to have force applied actually down on this face. I'm just going to flip it so our force is pointing down, and obviously you can see we can input whatever force value we need down there in the value box. Next, I'm going to fix one of the faces. I don't want this face to move. I want it to stay stationary, so we're just going to fix that one in place. Once you get all of that applied, we can then go in and hit Generate. And in the Generate option, we get to pick our study quality. We can slide that up and down. You select how we want to reduce our mass by maybe a percentage or a target mass that we want, and then factor of safety, and we would hit, obviously, Generate. I've already got this done. It does take a little bit of time, so I'm simply going to turn that on. So we can see it there. I'm going to hide these other constraints we've applied. And we see our results. And if we go ahead and turn back on the background components, we can see how it preserved those holes we selected, but it removed geometry to make this more lightweight, yet still strong in the way that we need it to be. If we turn on the stresses, we can then also see kind of where maybe some of the weak points are, and we could decide, maybe I need to preserve some other regions over in this area so we don't have such high stress there. So you can go back in and run the study again and get a different body, and you can pick and choose which one you want to use. To use this actually in our assembly then, we need to detach the body from the study. It's currently just a mesh body. It's just construction geometry, so I'm going to detach it. That will allow me then to come in and convert that construction body to a solid body. So I'm going to right click and toggle it to Design. And the other body, that square one that we started with, I'm just going to toggle that to construction so we don't have to see it right now. And then there we go. We can see our solid mesh design body. We're going to take a look at another example for that. We'll zoom in on this part up here. I'm actually going to open this guy up. We're going to do another generative design study here. So I'm going to pick a material this time, maybe just a steel. We'll hit Create Generative Study. And now again, we get to decide where we want to preserve regions, where we want to apply forces, and I'm going to put a force going through the center of this hole with an offset of 2 millimeters, just so we ensure we get the outside faces of that cylinder as well. Same thing with the fixed constraint over here on this side. We'll do an offset there as well of 2 millimeters. If we go into the Generate window, I'm going to just slide this all the way down to the lowest setting, just so it goes a little faster for you guys to see it, and we'll choose to reduce the mass by 15%. And if we hit Generate, it'll go through and generate our generative design. So what it's doing, it's meshing the model. So it's doing a simulation type solve. It's tessellating it. Then it's going to go through and try to optimize that and reduce the most amount of material that it can, while still maintaining that factor of safety that we needed to maintain the yield stress that we had in there as well. So there we go, it finished. We can see that it pops up a little window saying that maybe it couldn't go through and optimize every little face. There are some small corners or things it couldn't do. That's okay, we'll just hit close on that for now. And we can see our finished part. So pretty cool. We can then go in and show the stresses. We can see where the highest stress points are. If we're not happy with that, we can always go back in and regenerate the study, adjust some of our inputs, and get a new design. Just like with the last one, I'm going to detach that finished generative body from the study, convert that construction body to a design body so that we can then see it and use it back over in our assembly. So that's now our design body, and if we head back over into the assembly, there's that finished generative design model. So some really cool stuff here. I've had some time to be able to 3D print some of these parts as well, which is awesome. This works perfect for that. So hopefully this will give you guys maybe an idea of how to reduce mass on your parts, where you can remove material from, and how to end up with some really cool parts. So our next topic inside of ST10 is reverse engineering. I know a lot of people have been asking for this for a while. It's now here. It's included inside of ST10. This is available on ST9 as a beta add-on, so you can go down today and download this and add it into ST9 and try it out. But they are working on it more. It'll be added here in ST10. It's really great. You guys will be able to bring in and kind of reverse engineer some parts, any 3D scan data, anything like that. We can bring it into Solid Edge. We can build surfaces on top of it, and we can use that inside of our models. So the solution here, again, inside of ST10, we take those STL mesh files, 3D scanned in data, point cloud data, and we can convert that using some commands here that are built into reverse engineering. We can import the mesh, we repair the mesh, we then analyze it and identify different regions on top of it. From those different regions, we extract surfaces. After we get all of our surfaces extracted, we then do some surface trimming and stitching, and we create then a solid model. Here's a couple examples of what that kind of looks like. Starting on the left, we have a scanned in model of a bottle. When we bring it into Solid Edge, we can run some of the reverse engineering commands to automatically identify different regions, things like cylinders, spheres, flat surfaces. They'll be painted different colors. We can even include areas we don't want to identify, and in the second picture you can see some of the rounds, how they're the white color. We're not identifying those. We don't want to extract surfaces in those locations because those are more type finishing features that we can add in later on. After we identify the regions, we extract the surfaces that we see in the middle picture. We trim them up in the next picture, and then we can stitch it and convert it to a solid model and add back in those finishing features. Another example, maybe of a die here, scanned in data at the top left. You see the different regions that have been identified, the flat surfaces, the curved surfaces, and so on. Next, we go in and we extract the surfaces. We trim those surfaces, and then we end up with the solid model. So here we see the reverse engineering ribbon, or the reverse engineering tab in the ribbon, and we have a couple commands. We go through and we open up our STL file inside of Solid Edge. Then we try to clean up the mesh by deleting any unwanted surfaces or intricate mesh that might be hard to identify as a region. We fill those gaps in with the fill holes command. We can then run the identify regions, doing the automatic or the manual option to identify planes, cylinders, spheres, B-spline surfaces, etc. We then extract surfaces using the extract command, but we can go in and fit surfaces manually as well. Then we'll trim those and modify those using your standard surfacing commands, and then stitch it together and create a design body. So some really nice commands here that allow us to work with that STL data. So we're going to go ahead and take a look at an example of that. For our example, we're going to open up actually an STL file. So I'm going to go into my folder here and select an STL file, and we're going to open that up just in a ISO part template. And we can see the part file here. So it's mesh data, and what we want to do is take that mesh or STL data and make some changes to it. So one of the first things we want to do is maybe delete this mounting hole up here at the top. So I'm going to zoom in on that, and we're going to choose the delete mesh command, and I'm simply going to fence select what I want to delete. I just want to get rid of that entire hole, and we'll accept that, and that's going to cut all the way through the model and cut off that hole on both sides. Then we want to fill in the holes of that we just deleted, so we're going to run the fill holes command. This is going to automatically find those holes that we just created. We can choose how we want to fill in the holes, if we want them to try to be tangent to the existing geometry. Left there, linear, curved, whatever we need to do. So I'm just going to leave it on tangent and accept that. And it fills in our holes. So we can see those filled in on both sides of the model. Now what we want to do is we want to actually extract some surfaces from this so we can maybe mount it in an assembly or use it for something else. So there is an automatic option, but we're going to go in and do a couple manual region identification here. So I'm going to go in and identify the region on the inside of the cylinder. So I'm going to do the manual identify. And really easy to do. You're basically just going to paint the surfaces. So I'm going to paint how deep that hole is, and I'm going to paint all the way around the inside circumference of the hole. So I'm just going around painting those. You don't have to paint the entire face, as long as you get kind of the overall size, the circumference, the depth, and accept that, it'll figure out then the cylindrical surface you want to put on top of that. So we've got our region identified. We're then going to fit a surface to that, and we get to choose what type of surface we want to fit: a plane, a cylinder, sphere, etc. And we want to do a cylinder. I'm going to pick up that region and accept it, and it will automatically then create a nice little cylindrical surface for us. Alright, we're going to do one more. We're going to paint this outside face here as well. So I'm just going to go around the outside. We'll accept that, and then we're going to fit up just a planar surface to that one. So do fit again, leave it on plane. We're going to select that surface and accept it. And now we have our two surfaces. So we see if we toggle that on and off a little bit, you see how it fits perfectly with that STL data. We can then go in and use something like intersect and trim these two surfaces. So we'll get rid of the middle and that extra little piece. And there we go. There are surfaces that we can now work with. Again, use this to mount this maybe in another part file, something like that. So some really cool options there with the reverse engineering. So as you saw during reverse engineering and generative design, I may have mentioned something called a mesh body. That is new for ST10. We're able to work with mesh bodies. We can do add and subtracts from them. We can also do Boolean operations with them. So having this functionality to be able to work with the mesh-based modeling is really what's new in ST10 and allows us to do a lot of the new things. The mesh bodies, they're available downstream for use in assembly and draft files as well. And like I mentioned, we can do the Boolean operations. So a little more information on the Boolean operations. They are available in ST10, although the target body has to be meshed to be able to do this. Now, we can actually take existing design bodies and convert them to a mesh body to be able to do this if we want to. When you run the convert to mesh body command, you're going to get an options dialog box that appears. That allows you to pick your conversion tolerances and your angles of how you want that mesh body to end up as. When we convert it to a mesh, what you're doing is basically tessellating the body. You're adding a bunch of little faceted triangular surfaces all over it. So this allows you to adjust that tolerance and how accurate you want it to be. The nice thing about this is if you do this in the ordered environment, we can always roll back because it's history based. So if you are working in synchronous, I would suggest waiting to the end, transitioning into ordered, and then doing your convert to mesh body. Some of the rules, if you're going to try to do a Boolean with mesh bodies, is if your tool body is mesh, your target also has to be mesh. If your tool body is a classic BREP, so just a regular solid edge file that you've always worked with, your target has to be, or can be, a solid edge body. But we can also have a regular solid edge classic BREP file as the tool, and then the target can also be mesh. You can't have, though, a mesh tool body subtract from a solid edge classic BREP target body, so just keep that in mind. Some of the capabilities of the mesh command, in assemblies we can add assembly features to it. We can do things like mates and drafting. We can add drawing views, section views of them. We can do some interference checking, goal seek, zebra stripes. You can also pattern and mirror mesh bodies as well. Some of the restrictions of the mesh body don't really have the functionality to add dimensions to them. The mesh features are not editable in synchronous because it is made up of a bunch of little faces. There's no way we can push and pull that with the steering wheel. A lot of the recognize commands won't work either, so if you're in synchronous and you want to recognize holes, recognize patterns, those will not work. Same thing in the ordered environment. If you try any of the resize or delete commands, those won't work either. So just keep that in mind. And let's go ahead and take a look at this and see how this works. We're going to open up another file. And I have a part file here that is actually just a mesh body, and then we also have a solid body in it as well. I'm going to switch back up into synchronous, and again, this is just our mesh body. We want to go in and make some changes to it. I want to add maybe a hole to it, so I'm going to take a look at the front view here, and I'm going to sketch just a circle to begin with. And We're going to make that a diameter of 12 millimeters. We're going to dimension that off of our base coordinate system. And then since this is synchronous, I'm simply going to grab that region and then cut it all the way through the model. And again, this is just a mesh body, so it's just faceted imported data maybe. We want to go in and just do a cutout. We can simply do that by drawing a hole and cutting it through the model. And there we go, we've got our cutout. Now if you hold your cursor over it, it will say in the flyout that it is mesh. So it's not an actual hole. We can't go in and change the size of it. It is a cutout though in the mesh body. Another thing we maybe want to do is add some text to this guy. So I've got a reference plane already created. I'm going to lock onto that and just draw a sketch line that we're going to use to add some text. So I'm going to do maybe a part number that we want to add to this guy. We'll center that up onto our sketch line. And then I'm going to go in with the extrude command and select our sketch we just created. And we're going to add that geometry down into the model. And there we go. So we can go ahead and turn off our sketches in reference plane, and we can actually add geometry into it as well. Now, to do one of the Boolean operations, I'm going to switch over here into the ordered environment, and we have a second design body that I created, and that's what all of these features are that we see listed here in the Pathfinder. They're to create this body here. This was created in synchronous, and then we did a convert to mesh. To do that, you simply right-click on one of the bodies, and there's the convert to mesh body command. So it's already been converted, so we have our two mesh bodies. We can simply go up and do a Boolean subtract. I want to subtract from the top body, and I want to use the bottom mesh body as our tool to do the subtract from. And there we go, we see our cutout. If we hide that second body, we can see the cutout a little better. Now I have a PMI dimension attached to the original synchronous part. We're going to use that to change the width of the cutout, and that's actually going to drive the cutout here in that mesh body as well. So this is really kind of the best functionality of doing that convert to mesh. Maybe create your tool that you're going to do a Boolean subtract with in synchronous, transition over into the ordered environment, and then do your Boolean operations. So with convergent modeling here and being able to work with mesh bodies, we kind of get the best of both worlds. We get the best of the imported STL data, the best of the solid edge data. We can bring it all together and do whatever sort of modeling that we need to do. Alright, the next thing we're going to take a look at is CFD. So what is CFD? CFD is Computational Fluid Dynamics. It's a virtual simulation of fluid flow and heat transfer. So we can look at different fluids like liquids or gases. Now inside of Solid Edge, this is actually called Flow EFD. That's the name of the program, and E stands for engineering. So Flow EFD, it is a general purpose CFD software. We see some examples here of the different types of analysis that we can do inside of the software. I've got a slide here in just a second that'll be more descriptive of the different types of analysis we can do. The nice thing about Flow EFD though is it's actually built right inside of Solid Edge. If you've used the regular simulation inside of Solid Edge, it works similar to that. It looks similar to it, so it's really easy to use. And I've enjoyed playing around with it and being able to test it out. So the Flow EFD, again, it's a general purpose CFD software. We can do fluid flow and heat transfer analysis, and it's embedded inside of Solid Edge. So unlike all the other CFD tools, this one are going to be augmented by analytical empirical models, which make it easy to use for a wider range of users, including myself. Basically what that means is it's easier to use, it gives you faster answers with a high level of accuracy. The nice thing about it is we can use it at different design stages. So as you start to develop the model, you can go in and do different analysis and determine, what changes you need to make as you develop your parts or models. There's a wide application, a wide range of applications, and I've got a couple of those here. We can find things like pressure drop, so if you're looking for filter or pump efficiency, heat transfer if you're trying to cool electronics or a heat exchanger, mixing processes Maybe you're doing injection molding and you want to see how things are going to mix. HVAC, furnaces, combustion, flow fields for cavitation prediction, intake and exhaust manifold design, and even some force prediction. So really cool software. I believe we might take a look at this in a future lunch bite. If this is something you guys are interested in, send us a message and I'll be happy to answer some questions. And if it's popular enough, again, like I said, I'll do a separate lunch bite on this topic. Some other things that were new inside of ST10, some things on the manufacturing side. We've had some enhancements made to CAM Express, some new functionality added in NX11 to that with adaptive clearing, which is really useful. It makes your machining times faster. But there is also a new cloud-based hub that is being worked on to help out with your post-processing. So you can look up the different types of machines that you might be using and see if a post has been developed for them. So some really cool stuff there coming in the future. Technical publications as well has been added in ST10. So we have Solid Edge illustrations, which we can quickly create just some detailed illustrations of the designs. We also have Solid Edge 3D publishing, which allows us to create interactive catalogs, manuals, work instructions, anything like that. So some really easy to use software here. It's associative, so if you make any design changes, all of your manuals will update automatically for you and save you a bunch of time there. On the Teamcenter side of things, we now have part classification. It's supported through Active Workspace. There's a work offline mode where we can work offline at a customer site, come back to the office and synchronize any updates you might have done. The user interface has been improved inside of Solid Edge, so easier to work with. And then for anyone looking to get into Teamcenter, there are some new bundles provided as well. For the built-in data management side, we've had some enhancements made here. We had some enhancements to revision management. We have faster access to our associated drawings with a new Open Drawings button. We've improved the Design Manager utility. It just helps reduce some time spent on all of your tedious data management tasks. You can now do a full text search in all of your drawings. And it's now a little easier for admins in IT to set this up and get it up and running. So I'm going to show you actually a quick little demo of the built-in data management. So in this example, obviously you can see our assembly has many parts and sub-assemblies, and we want to make sure all the parts are the latest revision and that they're released for manufacturing. So we're going to change the display configuration to take a look at the internal components, and then we're going to run the get latest command from our data management ribbon. So the parts that have the latest revision available are highlighted. These are the ball clamps that we see here in red. All the other parts are ghosted and are made non-selectable. So what we can do is we can turn off the display of the ghosted parts, as well as some options to toggle between highlighting all parts with later revisions or only those with the latest revision status. We can individually select the parts we want to replace with the latest revision, or we can do it for all the parts. And then we can also see in the Assembly Pathfinder that the ball clamp is now revision B, and the red check shows that it is released. The next thing that we can do is create a new revision of the subassembly that includes that clamp. The revision command, it provides exact control over selecting and revising the parts and the assemblies and drawings. So we're going to use the new option to create a new revision of the subassembly. And you can also see here that the draft file, it is also changed to the next revision level. Towards the back of the assembly up here, we have a guide model. It's another part that was highlighted when we ran that get latest command. It's flagged with an icon in the Pathfinder that it's not up to date. So we can select that part if we want to, and we can run revisions again, and then we can get in and actually see the complete revision history of the part. The nice thing about this is we can display thumbnail previews of the revisions. We can also see there is a released revision B available, and we can select that revision and replace it. We can also pick then if we want it to replace the individual occurrence or all occurrences in the subassembly or the complete assembly. You also have the option to create a new part instead of a new revision when performing that replace operation, and we're actually going to do that here for the bracket by copying that existing component and applying a new part number for it. Now the nice thing about this is a new drawing is also created at the same time. So using these revision management tools, we can easily create individual records of a machine or piece of equipment as it was delivered as a customer and keep track of the machine as it's maintained and customized. The new part number that we set up, it can be generated automatically using the assign all option, and that's going to help us eliminate the possibility of duplicate file names and part numbers. Now when we're actually here inside of the part, we can use synchronous technology again to easily make any sort of required design changes. And in this example, we're going to quickly remove the holes and modify some of the geometry of one of the flanges. One of my favorite new buttons for the built-in data management is the Open Drawing button. This will allow us to directly open the associated drawing for a part, and here we're using it to open the drawing of the bracket and update it to incorporate the new design. And you'll notice also down in the title block it's automatically updated to include the new part number. So the built-in Solid Edge data management capabilities help users to make design changes easily without having to be too restrictive and without requiring complex and expensive software. What we're going to do next is actually open up another subassembly and use the Design Manager to work on this model. We're going to start with finding duplicates to see if there actually are any duplicate file names or part numbers. Obviously this can arise when maybe this is brought in from an external supplier or vendor, or it's an old design project, something like that. So the absence of any green check marks over on the left, that indicates that there is at least one duplicate file. The top line over on the right hand side shows the file was used in the assembly. The line underneath shows where the duplicate file is located. Our duplicates, they can be due to, again, the same file name, same document number, but we also get some nice additional data in the dialog that lets us determine if we're using the correct file by seeing if there's an associated draft file, when it was last saved, etc. So if the duplicate found is actually the correct file, it can be easily replaced into the assembly. So the built-in data management capabilities, they're standard. With Solid Edge, you can start using them after running the Windows indexer on the folder where you store all of your files. We have instructions on how to help set that up. Just reach out to us if you need some help with that. We also have a built-in data management lunch bite that you guys can go back and review as well. The last thing I want to talk about is the portal, Solid Edge portal that they're working on. So this is still in alpha or beta right now. Still just an idea, but it should be out later this summer, hopefully for testing. But basically what it is a multi-platform browser-based view and markup type tool. So we can go in and upload files like you would with Dropbox or Google Drive, anything like that, and securely house all your files online. But then you actually have a built-in viewer, so anyone can get on there, log in, view any of your part files, your assembly files, download and use the files that they need. It's just a really nice tool to be able to access your files wherever you need them, whenever you need them, and let anyone else have access to be able to view the files as well. So look for that hopefully later on this summer. And really, just to kind of summarize everything in today's lunch bite, the main intent of ST10 was to kind of fill out the entire Solid Edge portfolio. So we have things added not only in the design side with generative design, reverse engineering, convergent modeling, but also in the simulation side with FlowEFD, manufacturing, some new options with CAM Express. With the generative design, we can even do some additive manufacturing, some 3D printing. Technical publications with Solid Edge illustrations and documentation, some enhancements to the Solid Edge built-in data management and Team Center, and coming soon the Solid Edge portal, and then as always the hundreds of powerful apps that we have available to you guys as well. So again, that was the main focus of ST10, to really fill out that portfolio and get you guys what you need. So that's all I had for you guys today. Hope you enjoyed it. If you guys have suggestions for future Lunch Bite topics, please send them to me in an email address. I hope you enjoyed it. If you have any questions, again, please let me know, and have a great day.
Ally PLM.